very happy to give a seminar in Berkeley. And maybe I want to visit physically Berkeley, but maybe that will be quite near future. And so in today's my talk, I'd like to talk about a new generalization of entanglement entropy, which we call pseudo entropy, which is kind of in quantum information theoretical sense, I can say this quantity is a kind of weak value generalization of entanglement entropy. I will come to the definition in detail later. And this work is based on the our recent papers, like listed here, and based on the collaboration with Ari Morabashi, who is a postdoc in our institute, and Yoshifumi Nakata. He's actually quantum information theorist in Tokyo, and Yusuke Taki, our graduate student, and Kotaro Tamaoka, who is our postdoc, and Disha Wei is our graduate student. Okay, so let me start. Okay. So let me begin with the introduction. So as you know, so quantum entanglement basically means that in quantum mechanics, there are some quantum correlation between bipartite system like A and B. We just separate, for example, we take a pure state and just separate Hilbert space into A times B, factorize the Hilbert space, then there are quantum mechanical correlation between A and B. And a typical example is Bell state. If we talk about some spin system, so we have one spin A and another spin B. And if we think about this kind of state, then if we measure first spins up, then immediately know second spins down. And if first spins down, A spins down, then we immediately know second spin is up. And this Bell state gives some kind of minimum unit of quantum entanglement. This is a unit of quantum entanglement. And especially we focus on pure states. And that case, the story of quantum entanglement is very simple. So we say there are no non-zero quantum entanglement if the quantum state AB is not factorized into direct product between A and B, A times B. That's the case. If they are factorized into direct product, there are no quantum entanglement, there are no correlation, just factorized. But if they are not factorized, like because in quantum mechanics we can allow some linear superposition, so that case we say that quantum entanglement. And the best measure, at least for pure states, the best measure for quantum entanglement is entanglement entropy. And basically, this measures the number of Bell pairs between A and B. And let me give some two definitions of this. I think that many of you are probably familiar with this. And so one definition, this is mostly popular in high energy physics, and string theory, and quantum field theory. So we divide and condensed matter physics. And if we divide quantum system into two parts, total Hilbert space is HA times HB. And we talk about so-called reduced density matrix. We trace out some part of the space. That this we can imagine some spin system, a lot of spins. These greens arrows are spins, and we just decompose A and the other regions B. Then we trace out some region B. So this is just if we specify particular spins that precisely specify the Hilbert space of spin. So we trace out B, and we start with some pure state, and we trace out it. Then we get some rho A, which is the reduced density matrix, and we can just calculate the von Neumann entropy, and this gives entanglement. This is a definition of entanglement. And we can take some continuum limit. Sometimes this is subtle, but if we just naively think, just lattice constant goes to 0, then we have some continuum quantum field theory, and we can just decompose Hilbert space A and B. And the point is that we just need to specify the boundary of A to specify this A. So this is a normal definition in high energy physics. But in my talk also, the second, actually, the other definition, actually this is much more standard in quantum information theory, is more also very useful. So this is an entanglement entropy defined from so-called LOCC procedure. This is also, you can see this in a textbook, quantum information textbook. And so we can have, for example, just some spins, a lot of spins. Then first part is called A, first group of spin called A, and the other part is B. Right, then we have a total Hilbert space is HA times HB. And the LO, and we define LCC. LO means local operations. This is normal quantum operations, which act only on A or only on B, right, separately. There are no quantum communication between A and B. Just we act some unitary operation or projection measurement on A, also B, independent. This is the LO, local operations. And CC means classical communication. So we can send some signal by classical method, like just calling telephones and the fax and the emails. Classical information. We can send for between. We can communicate between A and B. Classical information. And typical example of LOCC is probably quite well-known example is a quantum teleportation. In that case, we use LO and CC and send some qubit to the other part who are far away. So A and B are quite far away, and we cannot do any quantum, elaborated manipulation between A and B. But the A and B are laboratory, so they can do some very quantum operations. So this is a basically physical also setup in remote A and if A and B are remote regions. And by using this definition of LOCC, so this is text of quantum information theoretical definition of entanglement entropy is to measure how much Bell pairs we can extract from a given system. So we start with some quantum system, let's assume some spin system, which is very complicated. They are entangled very complicated way. We are interested in entanglement between A and B, but they are entangled very, very complicated way. And we act some LOCC, so that's the one. And then we can see that we can always pick up some number of Bell pairs, but there are many kind of ambiguities. So what kind of LOCC you are acting? So we maximize number of Bell pairs, which we can extract by LOCC. We take a maximum, basically. This N is maximum. And so if we assume that maximum value, so then we take a following ratio. So even if we assume this maximum value, it's kind of a discrete number, but we want some continuous value, right? Von Neumann entropy is continuous value. So in that case, we take a so-called asymptotic limit to make the result improve. And so we start with infinitely many copies of original system. So like times m, like m is goes to infinity. And then, so such a very big system, so we act LOCC and how many EPR pairs are extracted. This is maximum number is n, and we take just ratio. So for each copy, how many? Right? We just take average and over m, and take m goes to infinity. And this is the definition of basically how many EPR pairs we can distill from. This is called entanglement distillation, and it's from some given system, but there are very famous theorem known in quantum information literature. I will come back to some kind of simple derivation of this, some simple case. And so if we properly calculate it, then we know. So entanglement entropy is precisely equal. This S rho A is just this one, von Neumann entropy. So this is a kind of operational way to understand quantum entanglement in a quantum system.
I'm not.
Yes, yes.
It's to. In order for this equality to apply, is that AB system has to be pure? Or?
Yes, yeah, so yeah, that's right, yeah. Okay. This is pure, yeah, AB is pure. We assume everything is pure. If we go to mixed state, the story is very complicated. Yeah. The reason, when this is pure, then there are very nice things, because I didn't talk about this way, so we can we distribute some number of pairs, but we can also recover original system. This is called formation. We can start with n Bell pairs, and we can reconstruct original system by LOCC. And there are some kind of reversibility happens for pure state, but for mixed states, this becomes irreversible. So this makes also definition very complicated. And actually, if we just look at some very axiomatic way to define entanglement, there are infinitely many different definitions of quantum entanglement, amount of entanglement in mixed state. So yeah, we are focusing on a pure state.
Right, thanks.
Yeah, thank you very much. Also, my talk, I always focus on pure state. Our story can be generalized mixed state, but more complicated. I'm not going to talk about it. Yeah, so now I come to holography. So we use just ADS CFT basically. ADS gravity on ADS is dual to boundary CFT. And I would like to talk about holographic calculation of entanglement entropy. And so I will first give some basic, very brief review of version 1 and version 2. But we want to, in this talk, main part of this talk, I want to give some version 3. So this is a new version. That's what I want to talk. So let me start with version 1. This is just statics. We talk about static space-time in ADS CFT and calculate entanglement entropy. So this is basically just minimal surface formula. And very simple. We just take out just one minimum. And we talk about the untitled space, and we have a region A and region B as a boundary. And the point is that this is a static space-time. We can take a time slice, t equals 0. So everything is Euclidean, like hyperbolic-like geometry, asymptotic radius geometry. And then there are nice minimal surface, and we calculate this area, and we divide by 4 digits, like Bekenstein-Hawking formula. And just minimize it. And but there are one more constant, topological constant, that this region A is homologous to gamma A. And this gamma A is a minimal area surface, codimension 2, and on time slice, and such that the boundary of A is the same as boundary of gamma A, and A is homologous to gamma A. So this is a static version, like, and now I go to time-dependent version. And this is covariant holographic entanglement entropy. So we are now talk about the Lorentzian time evolution of untitled space. And you can imagine some black hole formation or such a more complicated geometry. So generic Lorentzian asymptotic ADS space-time is, we know that it is dual to some time-dependent quantum state at some fixing particular time. There's some quantum state psi t in dual CFT. And this, if we calculate minimal surface, but this case we have to be careful because this is a Lorentzian geometry, we cannot minimize area. So we extremalize area. So this is extremalization. EXT is extremalization. So we are just talk about saddle point of area functional. And but we can find some solution. But if there are several solutions, then we just take a minimum one. So again, we take a minimum. But if we just calculate this area, so this computes this entanglement entropy for this time-dependent reduced density matrix. This boundary of A is again this boundary of gamma A, and A and B gamma A are homogeneous. This is actually based on my work with Veronica Hubeni, but this proof of this kind of formula is given by Don, Lukoitz, and Maldacena, and also generalizing this Lukoitz Maldacena analysis. Okay, so now I'd like to give a final question. This is actually related to my talk here, and so this is about. So the question about the Euclidean time-dependent background. Previously, we talked about this Lorentzian time-dependent background, and this is actually Euclidean time-dependent background. So we are talking about this minimal surface. So in Euclidean asymptotic area space-time, always we can define nice minimum area surface. And this is in asymptotic areas, and we are talking about Euclidean time-dependent asymptotic areas, and what's the meaning of minimal surface? This is well defined, quite well defined. So, but so what, of course, maybe this is not entanglement entropy, so we should ask what kind of quantum information quantity is this guy is dual to. So this is my question. Okay, and so, but probably this is much like entropy because anyway, always area divided by 4 digits. But what kind of entropy? This is a question. So this is a basic guiding principle. First of all, we should seek ADS-CFT for Euclidean time-dependent background itself. So we have some Euclidean time. Tau is a Euclidean time. So tau minus infinity and plus infinity are there. You can imagine some time evolution, Euclidean time evolution, but we can insert some operators. 2 operators initially, and finally we insert 3 operators. Then obviously we see, so if we take some tau equals 0 time slice, and we can define one quantum state by path integral from minus infinity to tau equals 0. So this defines this quantum state psi. And then we can define the other state plus infinity to tau equals 0. This gives a bar phi. Define this is a Brown located. And they are different. Point is that final state and this initial states are different. So this is a typical in Euclidean setup. In Lorentzian case, we use initially we create the initial state by Euclidean path integral, and then analytical continue to Lorentzian time, much like the Schwinger-Kirdesch-like description. In that case, states are just unique. But the Euclidean case is actually in the middle. If we pick up some particular time slice, they define 2 different states because Brown located in general different. This happens in Euclidean time-dependent background. So this is the first starting point. So what kind of, so that sense already entanglement entropy is not a good quantity because entanglement entropy is just defined for one quantum state. So we are just computing this area, but we are not sure this area is entanglement entropy for psi or bar phi. So that case, already we need some, probably we need some new quantity. And so our answer to this question, but this formula itself can be obtained by just repeating similar procedure for Liu-Koitsu and Maruda-Sena, for example, just derivation of holographic entanglement entropy by using replica calculation. Just to compute, rewrite gravity calculation in terms of CFT language, because path integral is dual to some ADS geometry. We know this dictionary. So so this is so naturally just obtain, and this minimum area. This minimal area. This calculates a foreign quantity. This is called pseudo entropy, which we call diffusion entropy. This is much like von Neumann entropy. S tau equal to tau log tau, but tau is not low. So tau is actually a transition matrix. This is no longer Hermitian. And this causes a new aspect, but also a very complicated issue. So this reduced tension matrix is just defined trace B of some original transition matrix. Original transition matrix is just here. If we assume psi and bar phi is the same, this is just normal pure states. This is inner product is just one. This is just normal reduced tension matrix, but now we are assuming two different initial states and final states. So this is more generalized non-Hermitian matrix, which we call just transition matrix because phi state goes to psi, bar phi goes to psi, and just a reduced version of this, and just correspond to low log low, right? On Neumann entropy like quantity. And not that this in general, so this transition matrix is not Hermitian, but this is also appears in earlier work of quantum information theory. Like they consider this transition matrix and define some conditional entropy, but here we define kind of analog of von Neumann. Okay, so this is the introduction, and so I go to the content. Just here, I just survey this contents of my talk. So we start with basic definition and basic property of pseudo entropy, and we give some results for pseudo entropy in qubit system. Then go to holographic calculation, and also we want to give some recent results based on numerical calculation, like free scalar field theory and also spin system. And we can have a nice correspondence, nice observation that somehow quantum phase transition can be captured by also this pseudo entropy in somehow new way. Okay.
Tadashi?
Yes.
Before you get going on the previous slide,
yeah.
This transition matrix is sort of a generalization of a global pure state, right?
Yeah,
and then
yeah,
you take a trace and you get. Is there some? Can you generalize this even further? Where the global state is there some analog of a global mixed state where this is already
yeah, good question. Yeah, actually, it's possible, but there are kind of many different ways to generalize it. Actually, so one is to one simple idea: we prepare some extra Hilbert space and purify it, and just define this way. And but the purification has a lot of ambiguities, as you know. So there are many. What kind of purification we can think about, and but this is a basic way. So we start with some assuming some purification, and everything just mapped to pure state, and then we can use this definition. This is something we had in mind, also in our paper. But maybe there are other clever way to generalize this to mixed state.
Thanks.
Yeah, thank you very much. Okay, and so okay, yeah. So but yeah, my talk is based. I'm focusing on pure state case, and we talk about these two quantum pure state, psi and bar phi, and this is a transition matrix, and so we decompose Hilbert space HA and HB as before, and we define this reduced density matrix, a reduced transition matrix like this, and then pseudo nth linear entropy. Pseudo nth linear entropy is usually defined from 1 minus n divided by 1 over 1 minus n and log of trace of log to the nth, and we just rewrite, we change it into transition matrix, and we get this nth pseudo entropy like this. And of course, n equal 1 limit just for tau log rho minus tau log rho, so which gives just standard pseudo entropy. And this quantity is not, but yeah, we have to be careful. This is not quantum state, of course, because it's depends on two states, and it's not a Hermitian, and positive, even not positive semi-definite. And in general, this quantity, pseudo entropy, is in general, it's complex variable. But in my talk, somehow we are focusing on Euclidean path integral, which with real valued source. Normally we get the real value, but in general, we can talk about some example which have a complex values for pseudo entropy. And if total system is, if A is total system and B is empty, so then, so we know we can easily see this is kind of projectile behavior, and this trace is just one, and always, or any Lenny pseudo entropy is there. This is a kind of, we know, similar behavior in entanglement entropy. Right? If we just pure state and just we covered all space A is total system, the entropy is zero. So, and similarly, we can show either psi or phi, only one of them is fine. So only one of these are no entanglement at all, but other guy can have an entanglement. But that case, this value is always there. But this anyway suggests that there's some connection to quantum entanglement already at this point. And so we can talk this, if we flip this psi and phi, we just compress conjugate because it's Brown case is flipped. And we have also analog of SA equals B relation, right? Tau A equals tau B. And if of course psi and phi are the same, this is just everything diagonal. Just potential matrix becomes reduced density matrix. So just this quantity just reduced to normal linear entropy. Okay, and one more comment is that in quantum theory, transition matrix actually arise when we consider post-selection. So post-selection means we start with some initial state, which is psi, and we talk about some operator, expectation value, but usually psi. Right? But if we sandwich with final state, this is kind of final state after this kind of post-selection. If we do just fix particular final state to be phi, then we basically calculate this quantity. And this quantity is no longer usual physical quantity because it's not, because this state is not Hermitian. So of course, this is complex. This is in general also, even if we start with the Hermitian operator OA, this value is not real value. So that says, of course, it's a bit non-trivial how to measure it, but the people, the famous work about this weak value, like this, and so we know nowadays people know how to measure this ideal part of this and the imaginary part of separately in some measurement, in quantum information measurement. But that ways. So this is called weak value. But in our case, what we are doing is roughly speaking this. If we imagine some holographic dual, so we know area operator, right? Basically, area expectation value of area operator is an entanglement. Area is just measure minimal surface. And in that language, we can say that this pseudo entropy is weak value of area operator. Like we just sandwich the state by so different state of diagonal area. So this is one interpretation. Okay, so now I'd like to talk about first example, explicit calculation, basic properties of pseudo entropy in cubic system. So because that this matrix tau A is not Hermitian, so we have to be careful and about its properties. And there are kind of classes which we did some classification. We just call general one, A, B, C, D, E. And basically E is the best one. For E, we have some nice quantum information theoretical interpretation. This case is both tau A and tau B are Hermitian. But nevertheless, this is not normal entanglement entropy because psi and phi are different state. These are some, I will come back, this has a nice LOCC interpretation, but there are some improved, slightly less constraint, like only tau A is Hermitian, or eigenvalues are just real, and just linear entropy is just real. And maybe holographic case probably corresponds to this purple one, this class B, because all entropy is real valued background, it's always real valued. But in general, we can create more general complex value of entropy. So I'm not going to detail about this exotic type of situation. I'm just mainly focus on this holographic case. These are just kind of distribution of pseudo entropy. It's just kind of numerical experiment. So this is a standard fundamental entropy. You have a nice peak. Right? So this is a kind of random state. We take a random state and total. So yeah, A is 8. That means 3 spins and it's 5 spins. And we take a random state, and then it's a sharp peak. This is also the origin of this page curve-like behavior. And for pseudo entropy, this peak is not sharp. Actually, there are peak, but it's not broader somehow. And the imaginary value also, yeah, this is the real value. Imaginary part is 0. There are some kind of peak, but yeah, not so sharp, I should say. This is just kind of numerical experience. Anyway, so this pseudo entropy is like for what we want to say is that first we would like to give some information theoretical interpretation of this pseudo entropy. So let's focus on this class E, which is this tau A and tau B are both Hermitian and the same positive definite, but they are psi and buffer is a different state. And then we can say the following thing. So pseudo entropy, now this is a real value. This is a real and positive, and this actually measures the number of distillable Bell pairs. I explained this for normal entanglement entropy case, but this is distillable Bell pairs, but as an intermediate state of post selection, psi goes to buffer. Initial state and final state is different, but just we talk about average number. So we take again this asymptotic limit. We should prepare infinitely many copies of original system. So let's see this in an explicit example. This is an explicit calculation. So we take a bar phi. This is just a 2-qubit system, and 0 is up spin and 1 is down spin as usual. 0, 0 state, A spin and B spin, and sine theta 1, cosine theta 1, and but this different angle, cosine theta 2 and sine theta 2. And then this is just plot of pseudo entropy. And this region is empty because it becomes imaginary. It's not, we eliminate that because we are talking about this class 3, which is the best property. So yeah, anyway, so if we calculate reduce transition matrix like this, and the whole element at this pseudo entropy looks like this. It's depend on theta, both theta 1 and theta 2, okay? And so, yeah, so and the way how we can proceed is just prepare M copy of original quantum system. This is actually very parallel with what people understand, right? Number of distillable pairs from qubit system, just same as derivation of this LOCC formula. And so we just take M copies of this, right? Cosine theta 1, and we can expand this binomial expansion. You can just expand by number of cosine theta 1, right? Sine theta 1 is k, and M minus k. S1 and S2 is like this. And then once we fix this variable k, we get a maximally entangled state, right? 0, 0, 0, 0, 0. So we can just expand only M times this is just 0, 0, 0, 0, 0, all 0. And that means k equals 0, 0, 0, 0. But if we have M minus 1 of them and 1 of 1, 1, then we just only 1, right? 1. So P, this has a 1, 1, 0, 0, 0, 0. 1, 0, 0, 0, 0, and 1, 0, 0, 0, 0. Or there are permutations. Right? So permutations gives them this extra index A. Right? First one, second one, it just change the location 1, right? Where are we in that one? Down spin. And that way we get some kind of EPR pair, right? Sort of generalization EPR pair, maximally entangled state here. And then we project to a maximally entangled state with log this combination number, M combination number, M. The number is MCK here. And so if we fix particular K, there are log MCK entropy, right? So log CK entropy, and with some probability, which is corresponds to square of basically this coefficient, PK. PK is just square, basically square of this guy. Like this, basically. Yeah, square or sorry. We talk about post selection, so we sandwich to it bar phi state. So we C1 and C times C2. Right? We have C1 is the initial state, and C2 and cosine theta 2 is about the final state. So we C1 times C2 appears. S1 times S2 appears. This is a probability distribution. And just take average. So then we can easily show by using saddle point analysis, and this is exactly, if we take a ratio of n and m, this is precisely pseudo entropy, which we define this way. So this is a kind of simple intuitive understanding of how we interpret this pseudo entropy in terms of quantum theoretical. But here, again, we just restrict to particular good class, right, where everything is real value, real positive value. So in general, we have to generalize this to complex value, which is still missing. So it's a quite interesting future problem. Okay, so these are some physical interpretations. So basically, this is the first example of qubits.
Can I ask one quick question?
Sure.
could you say could you explain intuitively that when this should entropy become real or complex?
Yeah. So basically, of course, from this example, because this cosine theta and sine theta is real, if these two guys are real, then it is real value. Basically, but actually, this is it's a subtle thing because even if everything is real, but we are missing this white region because white regions we have some kind of negative value. For example, this becomes negative, then some problem happens when we take a log tau log tau. That's case, right? If inside the log is negative, then a problem. So yeah, but roughly speaking, if the coefficient is positive definite, then also that is fine. And in quantum field theory, if we talk about Euclidean path integral with the real valued source, usually we get a positive value, positive normal value. But if this becomes some phase factor here, then non-trivial. Right? It's in general complex. Okay. Okay, so now I go to a holographic calculation. So, and then go to quantum field theory calculation later. But the holographic calculation, already I explained some essence of this calculation, but basically we take some time-dependent Euclidean background and we calculate minimal surface, region A and minimal surface. And yeah, this minimal surface in general, because time-dependent, it's in general not on a canonical, there are no canonical time slice in the Berkeley, it's just generally non-trivial shape. And so we can just calculate this quantity by area divided by 4G Newton, and this is always positive definite. And so this means that we are talk about very special state because pseudo entropy is in general complex value. But the basic property of this holographic pseudo entropy is if this is pure, this rho A is pure, that means A is everywhere, right? If A covers everything, then it's just we can shrink this surface to zero size and entropy is zero. And if phi and psi is not entanglement, actually this is zero. Because this is actually we can, show this is in ADS BCFT or just putting end of the world brain. So we can realize no entanglement by thinking of a boundary state, Kaji state, and then that is dual to just putting wall, right? Domain wall, right? Or just end of the world brain, just ending here. Space-time, this part is just missing, and this is the end of the world brain here, and just physical space-time. And then if we calculate entanglement entropy, so this minimal surface end on the end of the world brain, so it just, this length is just zero. So just because it's just A is just coincident with end of the world brain, so entropy is zero. This is also consistent, and we can easily also see SA equals B as the usual entanglement. This surface is shared also region B, and subadditivity also can be easily shown. But for example, one may ask, what about strong subadditivity? But this is a bit subtle because if we talk about time slice in this kind of zigzag-like, way, then it is easy to violate it. And yeah, this is actually pointed by very nice referee of this our paper. Actually, we missed this, but because of that, we need. If we don't have any requirement of particular slice, then strong subadditivity doesn't mean anything. But maybe we need to limit particular slice like straight line slice. Then SSA probably has some meaning. And yeah, also, yeah, as already mentioned, so we can derive this formula by Lukowitz-Maldasan like calculation generalized entropy. Like basically, this we can even if we talk about Brown Keto states different. So like we can put one operator here and another operator here, then phi and psi is different. We can just use normal replicatory. We just copy and copy and subsystem A is here. We put some cut here and we paste with each other. Right? So then we have N-seated Riemann surface with some O1, NO1 operators, NO2 operators are in that. Yeah, so this is a very brief survey of holographic calculation. So now I give some explicit example. This is one typical example is Janus solution. Janus solution. The reason is that so we need to prepare right initial state and final state is different. Initial and final state and Janus solution has a connect to different quantum state. So basically, Janus solution is dual to, we know this solution is, I'm talking about ADS3 CFT2. This is dual to exactly marginal perturbation, but in homogeneous way. So we have some exact marginal operator OX, but we perturb by amount of phi minus or minus tau region, and plus tau region, we perturb in different amount, phi plus, right? Phi plus. Maybe phi plus is positive and phi minus, for example, negative. That's also possible. So these two guys are different states. This path integral plus minus infinity to 0 is defined one state by this perturbation, psi plus perturbation. And the initial state is defined by path integral by this operator. So that way it's different, but the point is that we keep kind of boundary conformal invariance, some part of conformal invariance, because this is exactly marginal. So we have some ADS2 like foliation. There are kind of SL2R. So originally we have a SL2R times SL2R symmetry, but this perturbation preserves SL2R, only one part of conformal symmetry. So that we can, taking this advantage, we can construct an analytical solution. This is done by this Back-Gatt-Hirano. This is just this solution. So we can have some nice formulation. And anyway, so this is a nice solution. And phi changes its value like this way. So we start with phi minus, goes to phi plus. And by using this solution, we can calculate very easily. We can calculate entanglement entropy. Basically, we take term we call zero slice and calculate the minimal surface, our just geodesic length here. And so this is a profile, this is normal profile, this semicircle, and calculated. Now, non-trivial thing is coefficient changes. Usually, this is always 3/c, right? But this coefficient changes because of this perturbation, this gamma perturbation. Gamma is just basically this gamma is a deformation parameter, which means phi plus minus phi minus. Just this difference. If these two guys are the same, just the same standard ADS3 geometry. But these guys are different, so this difference is just gamma. So this is, and it's, and also interestingly, you can expand some perturbation theory. So using perturbation, gamma is smaller than it's like this, but from this formula, we can see somehow effective central charge, sort of central charge is decreased by this Janus deformation or this kind of the reason because these two states are different. This minus is actually interesting. And we can actually reproduce basically this behavior by conformal field theory perturbation theory by calculating this pseudo entropy. And also even more generally, if we talk about relevant or exact marginal perturbation, here it's exact marginal perturbation, but we can also talk about relevant perturbation. And if we act this on some CFT vacuum, psi1, this difference is always negative. And gamma square, it's also started from gamma square, but it's always negative. We can actually show this. So this is quite looks like a general property. And I'm also, in my talk, I'm very interested in this kind of difference, which is also coming in other calculation. This is also related to some quantum phase transition, as I'll come back. But it seems here, it's just simple perturbation always decreases pseudo entropy. But sometimes, some interesting case actually increases this difference. Okay, yeah, so now I come, so basically this is, I just finished the basic outline of pseudo entropy and just to give some explicit examples. So this is a free scalar example. So yeah, model is actually very elementary, so I'm not going to take some more time. I just give some numerical result. This is kind of Lipschitz scalar, so I just put also dynamical exponent z here. Normally this is z equal 1 for relativistic case, but sorry, this is not actually. Sorry, we just put, we need to, these are relativistic invariance, but sorry, this is some mistake, and it just lambda to this power or time direction. So lambda to this. And so M is a mass, and we can discretize this into lattice. And the idea is just to we have a two states, but this is just ground state for M1 and Z is dynamical, so Z1. And psi2 is a ground state of Hamiltonian with mass M2 and Z2. We just change M1, M2, Z1, and Z2. And we can calculate pseudo entropy. We can just follow standard approach of using correlation functions. So this is Gaussian. This system has a free Gaussian theory, so we can compute the entanglement entropy from the knowledge of 2-point functions. And actually, we can show the same, basically same thing true for pursuit entropy, but one non-trivial thing is this red part. We needed to use some complexified symplectic transformation. So in general, finally, we need to diagonalize some matrix or this correlation function matrix. This is also true in entanglement entropy. So we have to complexify transformation, but that is actually justified. And in the end, we get our interested case, we get the real value result, basically like this. But anyway, this is kind of numerical. In the end, this is technical part. And here are some plots. First one is a relativistic. It's a dynamical exponent, Z1, Z2, both of one. This is just a relativistic massive scalar, but mass is different, M1, M2. So then we can show that if we plot explicitly, basically, leading part, UV divergence same as what we know about entanglement entropy. This is logarithmic form, and central charge is equal to 1 with a free scalar. I'm talking about the 1 plus 1 dimension, 2-dimensional quantum theory on a lattice. And there are some correction. For example, if mass is very small, this is L is a subsystem size. We have some region A and B, and this length is LA, but the number of sites is NA sites. NA is number of sites, DA. And anyway, so this small L, large L is a total size. We impose some periodic boundary function. Total size is capital L, and small L is a length of subsystem A. And this is familiar formula, and some correction we can also calculate in some expansion of M, small m. And this is some plot. This is just basically log sine function, but it's depending on the different value of mass, right? Even though M1 is the same, but M2 is different, so the result is changing. So this is appears this correction, this kind of behavior. And we can have a more general case because we introduce Z, which is a dynamical exponent. So that case, if we change, let's assume Z1 and Z2 is the same and mass is different, then larger Z has a larger entropy. This is actually also, we know very much in entanglement entropy, because large Z means more, we have a more non-local entanglement because theory becomes more non-local, right? This is non-local, this becomes higher derivative theory has a more non-local. Non-local, that means entanglement is increasing. In the end, it approaches volume law, but it's here area. And also, first result basically says that this is in 2D and it's logarithmic correction, but if we can imagine even higher dimension, the Pseudo entropy also follows area, basically, in standard quantum physics. And yeah, also we can change the mass is the same, but we can change the Z. So then, so Z equal 1 as Z1 is always 3, but we can change Z2, right? There are, you can see some saturation behavior, right? So Z equal 1, Z2 equal 1, Z2 equal 2, but the Z2 equals 3, if these two guys are the same, then essentially saturates. But anyway, always large G has a larger entropy. And this saturation behavior is more manifest here. So this is the one which I showed it here, it's like this one. So as you change Z, so if we set Z equal 1, Z1 equal 1, then up to Z1, Z2 equal Z1, it's increasing, right? Z1 equal 1, increasing, but this one stopped. If Z1 is 3, then it goes until Z1 equals 3, but it stopped. And also mass is the same. We fix mass 1, M1 is to 10 to minus 5. So small mass has a larger entanglement, so it's very large, but it's saturated here, right? So if so larger mass is small entanglement, small pursuit entropy increasing, but are stopped at the value exactly same as M1. So this basically suggests that the pursuit entropy is bounded by minimum of these two guys, right? Minimum of entanglement entropy, rho 1 and rho 2. This is something we call the saturation behavior. But we can make this more precise. This is this difference. So this is, we can show, so here we plot this, basically this difference. Pursuit entropy minus average, we can divide this two, right? So pursuit entropy minus average of initial entanglement entropy and final entanglement entropy. This is always negative. This difference is always, you can see this negative for any case. Different to M and different to Z. So it seems this quantity is always negative in quantum field theory. So we got quite interested in this difference. And is this inequality is always true? So this is a question. So this is, then I go to my final part of the talk. So this makes, so yeah, it's good to study other examples. For free scalar, and this is difference is always negative or 0. If, of course, states are the same. If rho 1 and rho 2 is the same, psi 1 and psi, then of course this is also same. So just this 0 like this. Right? But if they are different, slightly different, it's always negative. And we can also justify this in exact marginal deformation, like this example. Like this example, we can also explicitly calculate perturbation theory and confirm this statement in general perturbation. But so then, yeah, so we can first study some very toy model, like 2-qubit system already. Toy model already shows that this is no longer true. This statement is not true. So here we talk about difference, but we assume these two states are very close to each other, right? And the small perturbation, but even small perturbation is coefficient can be also positive. So this positive, this peak is exactly the point where this qubit system is maximally entangled. So if we talk about the maybe volume law, like very strongly entangled situation, somehow this inequality also becomes positive. But we are talking about area law state. It's much smaller entanglement. Maybe that's the reason we have some negative value. This is one interpretation. And I'll go to one more interpretation. So here, this is my final part of my talk, and this is about the quantum phase transition. So next thing, this is very basic example is Ising spin chain with transverse magnetic field. So for example, entanglement, this is first thing we should compute. And so this is a Ising model. J is an interaction, Ising spin, and H is the external magnetic field. Let's check the H equal 1 because these two guys are just a ratio. We're only interested in ratio between J and H equal 1. And psi 1 is a vacuum state of particular J1, right? This J is J1. And psi 2 is a J2, right? And J is smaller than 1 is paramagnetic phase, and J greater than 1 is large interaction, then ferromagnetic phase. So that means J equal 1, we know there are famous quantum phase transition point. So this has a richer structure than free scalar theory. So then we plot this result for this difference. Right? Pseudo, we can compute pseudo entropy, but we plot this difference like this. And then, yeah, if we plot this, then we see, so, but sorry, we plotted this, either of this, both of this. So this pseudo entropy, this contribution is blue, and this normal average of entanglement entropy is this orange. So this guy becomes positive when this blue guy is larger than orange guy, orange plot. So this region and this region, actually this quantity gets larger. And this happens when psi 1 and psi 2 are different phase. If these two guys are the same, so if J1 is less than 1, so if J2 is less than 1, that's always, we can show always blue guys are situated below, like this. Also J2 is 1 is nothing interesting. Happen J2 because this region is always positive, I mean, this becomes negative. But if these two guys are different phase, this becomes positive. And so this is one interpretation, heuristic interpretation. If two guys are in the same phase, yeah, as already mentioned, same phase, it seems this is always negative. And if two guys are different phase, maybe sometimes this difference can be positive. And one interpretation, you can imagine some psi 1 and psi 2. This is Euclidean path integral, right? We are talking about this is Euclidean time. And we measure entanglement entropy. And if we assume there are some kind of gapless state between, because these two guys belong to different quantum phase. So in the border, we expect some gapless phase. And if there are gapless phase nearby, we have an enhanced degree of freedom. So it's quite natural that we get entanglement here is enhanced. This is one interpretation. And holographic interpretation is very parallel with this one. So this psi 1 of psi 2 gap to state, gap to phase. It's like ADS soliton, like confining solution. But if we talk about this, you can imagine some Einstein gravity coupled scalar field, and scalar field is phi 0 and phi 0 minus. And we can assume some G2 invariant metric configuration because this two, if we assume potential of scalar field has a G2 invariance. Just maybe phi square, m square, phi square is enough. And then along this border, we expect dual geometry has a phi equals 0 because it's situated in the middle. And then potential gets very small. So we get a massless, it's much like similar to massless situations, like we get to some untitled space here. But if we go beyond there, deep in the future or deep in the past, then we have some confining solution. So obviously, entanglement entropy should be enhanced here. And we can especially calculate this in Hamiltonian constraint of gravity background, assuming this G2 symmetry. So this is basically Hamiltonian constraint. And this is minus, this n is this normal direction. And the potential contribution gives enhances, the enhancement of this entanglement. But derivative becomes opposite. Because of this minus sign, we have some minus contribution for Janus solution, which I mentioned here. Sorry, it's going. This minus. This minus because basically there are no potential for Janus solution. It's exact minus, so always minus contribution. That's squeeze or that decreases Pseudo entropy. But the potential effect is increasing Pseudo entropy, and this is enhanced if this is true. So, and indeed we can find such example in holographic. And that case, Pseudo entropy is increased. So that way, if these two guys are situated in different phase, there are chances that the Pseudo entropy is increased. So here are conclusions. Basically, Pseudo entropy is the area of minimal surface in Euclidean asymptotic radius. And this quantity is in general complex value. But yeah, our case is non-negative because we are talking about Euclidean path integral with real value sources. And Pseudo entropy is for a simple state, non-exotic state, we give some quantum information theoretical interpretation, basically amount of quantum entanglement in the intermediate states. Right? The generalization to complex value is quite interesting future problem. And finally, we saw that the Pseudo entropy for ground state in quantum field theory satisfies, in our example, satisfies the area law. And we find some saturation behavior, and we are also interested in difference between Pseudo entropy and normal entanglement entropy. And if two states are connected continuously, then it seems this is negative, but if they belong to different phase, maybe this looks like positive, can be positive. And here are some future directions and quantum information meaning of this, yeah, already mentioned complex value of Pseudo entropy. And yeah, it's more interesting to explore more gravity duals, such that also this Pseudo entropy takes complex values. If metric, for example, complex value, then this is definitely true. And the constraints on quantum field theory, also we might be able to write like entanglement entropy derived C theorem, maybe we can find some interesting constraints of quantum field theory by using Pseudo entropy. And it's also interesting to talk about application to condensed matter physics and statistical physics. And finally, it's good to explore some implication to quantum gravity. Thank you very much. I think I'll stop here.
Thank you very much. Time for questions.
Can you say a little bit more about this? You may have said it. There was a lot of information, so I may have missed it. But can you say a little bit more about this fact that in general it's complex valued, but holographic pseudo entropy is non-negative? Could that be something like MMI or whatever? Some fact about holographic states that's special, or is it unrelated to that kind of consideration?
Thank you very much. Yeah, for the question. Let's see. Yeah, I think actually that aspect is also true for conformal field theory. So we talk about some replicatory like this, as usual. And we talk about some insertion sum operators, O1 and O2. And or maybe in holographical, we can insert some source, right? So that the initial state and final states are different. And but if operator O1 and O2 are real value, so I just put it to Hamiltonian correlation, but let's assume O1 and O2 are real, then we can imagine this correlation function of trace tau to the nth power, we can conform map to just a single plane and with 2 endpoint function. And this correlation function also expected to be real value because operator is real. And also in holographic case, not only we talk about this insertion operator, but also we can talk about just the integrated source. And if source itself is real value, external fields and also operator both are real, then we expect Euclidean path integral on replicate manifold itself is real value. And yeah, it is quite interesting. Yeah, this is Raphael's question about this implications in holographic speciality. It's quite interesting. And that can be seen in some explicit calculations in this kind of operator. So maybe I don't have time to explain this, so I just omitted. So, but I can just give some plots. So this is somehow we just insert this operator O1 or to some part. And here we plot delta S is this entanglement and pseudo entropy difference. We compute pseudo entropy and subtract ground state, just trivial contribution, just standard entanglement. Then CFT calculation is like always, for example, negative, use negative result. But if we calculate in holographic CFT, we have some non-trivial hump, some peak, and that they behave differently. But here, both of them are real value in this example. So yeah, of course, it's quite interesting to see how this holographic nature of very chaotic situation changes some basic property. But yeah, it's quite interesting. But so far, we didn't find some any definite answer to that question.
Well, I have a very naive question. So you got two states here. So if you have two states, then there is what's called a relative entropy between these two states. Right?
Yeah.
To satisfy all the nice properties. But I'm wondering if there's any relation between this and what you have defined here.
Yeah, good question. So I don't have any definite answer to that question, but basically something crosses this difference. This difference goes to zero if you talk about same state, like psi1 and bar phi the same, then this difference goes to zero. So basically this difference, if this is non-zero, that means these two states are different. And if two states are so different, then this difference goes to larger. But the difference between this difference and relative entropy is the relative entropy is always positive, right? Positive definite. But this quantity can be both positive and negative, as I explained. So yeah, connection probably non-trivial.
Okay, thank you.
Can I ask one extremely elementary question, probably just confusion in the simple setup? Can you go to like conclusion slide? Yeah, and then the middle one, pseudo entropy for non-exotic case. So it's the most minimal case. That's what I'm asking. And is it like this is a quantity? Let's take a Euclidean ADS, and that's inside this ball, and the CFT it's boundary, and then you slice it, right? You take a particular slice, and that defines a state for psi and phi clearly.
Yeah.
And then you just divide this slice equators into two parts, A and A bar.
Yes.
And then you first trace over, and then you define this law of law. And the claim is that corresponds to the area, minimal area surface anchored to A, right? So, okay, good. So if you compute this minimal area surface, and you're saying that this is the amount of quantum entanglement in the intermediate states. What's the intermediate? Because intermediate is at the same time or something. It's just I don't have any.
Anyway, yeah, okay. Basically, that's basically what I had in mind is this one. Basically, so we define anyway area operator and sandwich by these two initial state and final state.
Okay, so that's the meaning of the word intermediate.
Yeah.
No concept of time evolution, right?
Huh?
No concept of time evolution, right?
No.
Phi and the psi is at the same side, right?
Not like this. There are no Hamiltonian to time evolution.
Okay,
just this linear product. Yeah.
Intermediate sounded okay. That's
maybe
question of word.
Yeah. So we basically we insert some all complete set of state and basically the average of that.
Okay, basically. So it's kind of bit different from like a post-selection if you intuitively imagine a Lorentzian type post-selection, right? It's not like that. You just prepare two states at the same time.
That's right. I agree. Yeah. I just follow this, I mean, weak values, just follow terminology. But if we really want to estimate this in real experiment, we need a real time evolution. And that's, we need some different implement. Yeah.
It's probably more structure needed.
Yeah.
Okay.
Yeah, it's
great.
just very mathematical way of saying. Just very formal. Yeah.
Are you, this again, this might be just a confusion, but are you taking phi and psi to be in the same code subspace in some sense? Do they have to correspond to a similar geometry?
That's a very excellent question. I think so. I'm assuming that. Yeah. But of course, in general, we don't necessarily to restrict to that, but we can still define this quantity, this Pseudo entropy. This might not be defined, but this quantity is self-defined. But I don't know how to calculate in holography.
Yeah, that was going to be my next question. Yeah. Okay, that's interesting. There should be a generalization.
Yeah, that's maybe very non-geometric, but yeah, I think that's very interesting generalization.
How to patch the two space-time in the bulk is not trivial, right? Probably.
Yeah.
Because you have two states in the patching.
Yes.
The same.
Yeah. And we do it
sometimes
just
maybe
using,
possible, sometimes maybe
so.
not.
Everything is stringy, so I don't know how to construct such a geometry.
Well, maybe by Lorentzian evolution.
Lorentzian, yeah. But Lorentzian evolution is correspond to more normal definition of holographic.
So the thing is not like initial state and final state. This psi and phi is on the same equator.
Yeah.
That's why this intermediate state or something, those word is confusing. It's just
placed to each other.
Placed on top of each other.
And
so and then if those two states represent totally different space-time, then maybe upper half is some space-time, lower half, but it's then what's the slice? Can you glue it? All these things are minute you can get the bulk space-time, then probably you can compute the area. But how to come up with the
I would have thought that intuitively, if you try to compute anything using a gravity path integral, if the only way to get from one to the other geometry is by some time evolution through the Lorentzian or through some complex geometry, then that's what the path integral is going to tell you to do.
So it may not be possible.
Well, I think it might actually be possible. It just might not be possible while staying entirely in the real Euclidean domain. But maybe I'm probably I'm just guessing.
I see. If we go to outside, of course.
Well, that's the thing. I think you're saying like extension. If you extend this to be like separating psi and phi in time direction to really to mimic or to deal with the final state like projection, then may be able to do it, right?
Well, in the replica trick, we have to connect one, sheet to the other, and now the geometries don't match. So I guess you just have to interpolate,
Okay.
As long as the inner product is non-zero, in principle, we should be able to find a string review.
I was wondering what might happen if you took the initial and final states of massive quantum field theory to be the in states and the out states. So your overlap is the S matrix. And then you would be somehow trying to understand entanglement in the DS matrix.
Sorry. We
have you thought about that at all?
Massive. Here we studied massive scalar field with different mass.
You're looking at entanglement in real space, whilst this will be entanglement in momentum space.
I see. So that I see. Yeah, that's quite interesting. Yeah, we didn't look at that, but maybe. Yeah, that's because there are interactions. So entanglement also entropy is non-trivial. And I see. S matrix limited to particular kind of post-selected state. I think you're suggesting.
Yeah.
Yeah,
in a
yeah,
totally
exactly. But that's, so
different
yeah,
sort of
we don't have
question.
an immediate answer to that, but I think it's quite interesting to study it. Yeah, from this real space result, I think it's not easy to predict what kind of result we get.
I don't know if anyone's looked at that at all.
Yeah, some people looking at just the calculation of entanglement for S matrix. It's a standard entanglement entropy for scattering amplitude. Several groups are doing, but not this pseudo entropy calculation as far as I know.
Thank you.
Thank you very much.
More questions? If not, let us thank Tadashi again.